In this problem, we want to find the Thevenin equivalent circuit for everything external to our load resistance out here. So that means everything in blue we're going to simplify to a point where it's just a voltage source and a series resistor. And that seems like a tall order, but working with Thevenin's theorem, we can do this. So first off, notice you've got this 10-volt source up here and a negative 6-volt source down here. It might make you feel a little bit better to redraw the circuit so that you see that a little bit better. For instance, on the R1 side, I would just draw our 6-volt source like this. That negative basically means that if we have 0 volts ground down here, we would drop 6 volts before we get to R1, which is the 0.8 k ohm resistor. Now, right here, we have the 6 k ohm and the 4 k ohm connected. I'm going to actually just put the 4 k ohm down this way. As long as it's connected at the same spot, it can be on the other side, and it goes to a 10-volt source. So I'm just going to draw that in too, because sometimes it's nice to see that. And that also goes to ground. And then I've got my 6K, which goes straight to ground from there. And then the 1.4K. Might draw that down just a little bit. 1.4K right here. And of course RL, which goes to ground. Let me just connect all that up. All right, so this is basically what our circuit looks like. And we want to find the Thevenin equivalent circuit for everything external to the terminals A and B right here. So what I'm going to do first is remove the RL. It took a little too much, didn't it? Remove the RL, and then I'm left with just my terminals A and B. So step one, of course, is to find our Thevenin. And to do that, we're going to set our sources to 0. And then look in at the A and B terminals to find our total resistance. So here, so I basically shorted out the 6-volt source and the 10-volt source in my new circuit down here. So we've got 0.8K, 4K. I think I forgot to draw in what that is. That was my 6K right here. And 1.4K. So basically we're putting our ohm meter here, measuring at the terminals A to B. And so as you can see, we have 3 resistors in parallel, and then I'm going to add those to the 1.4. So my R Thevenin, which is our total in this case, would be the 0.8. Whoops, let's write that correctly, shall we? 1 over 0.8K plus 1 over 4K plus 1 over 6K, and then we're going to add 1.4K at the end. So when I do the math there, and hopefully you'll do this with me if you want to pause the video, you can do that, or if you just work quickly, you can do that. So that gives me about 2K as my R Thevenin. So not too bad there. Okay, second, the second thing I need to do is actually put my sources back and we're going to find E Thevenin. So put sources back and find V open circuit from VA to VB. So basically we're taking VA and subtracting VB, whatever those end up being. So I'm just going to redraw my circuit again really quickly here. And what do we have there? 4K into 10. Now at this point, there are probably a few different options for how you want to go about solving this. Remember, we just learned about mesh and nodal analysis, which would work here. 6. Okay, so now a few different ways we can do this to find our E Thevenin. Basically, if we're measuring from A to B, that would be E Thevenin. So how you want to go about this is, there are many different ways we can do this. We could do a mesh analysis. We could do, let's see, what else? We could do superposition to find that voltage there. We could do some source conversions. Like literally, there are several different options here. And I tell you what, let's do a source conversion. I don't think I've done that this way. Done this circuit this way before, but let's try the source conversion, because notice what we need. I'm gonna, you know, when you start using these tools, you start developing a feel for what tools you want to try for, you know, for what thing you want to do. Like I said, all of those would work just fine. But keep in mind, the current through that 1.4 k ohm resistor, when these terminals are open, that would be 0, right? So if that's 0, then really the resistor might as well not be there. Okay, so I'm just going to draw that so that we see that that 1.4 k ohm resistor really doesn't mean anything in our circuit. So if you're going to do mesh analysis or superposition or anything else, what you're really looking for is the voltage here across the 6K, because that's going to equal your E Thevenin. So as long as you can find that voltage, you can do use any of the tools in your toolbox. It really doesn't matter. I think I'm going to do the source conversions. I think that'd be kind of an interesting thing to do for this. And I'm going to convert this voltage source to a current source and this voltage source to a current source. Again, you can do mesh analysis if you want to do that at the same time that I do my source conversion. Feel free. So remember, that's going to give me a current source in parallel with what was a series resistor, and then a current source in parallel with, again, what was a series resistor, and then there's the 6K out there. Just be careful when you're doing your source conversions that you put everything where it goes. So for instance, I'm removing that voltage source here and I'm putting it right back in the same place. Okay, so 6 divided by the 800. Okay, so I've got 7.5 milliamps there, and then the 10 divided by the 4K, it gives me 2.5 amps, milliamps. Sorry about that, milliamps here, and that was 6K. So basically, if I can combine my current sources, combine my resistors, and find the voltage drop across that, that should be E Thevenin. So when I combine my voltage sources, I have 7.5 milliamps going down and 2.5 going up. So that means I have a net 5 milliamps down. And then I'm going to find my RT here, which is the 800 in parallel with 4K, in parallel with the 6K. Okay, so I've got 600 ohms there. So that means the voltage drop, or VT, would be that times the 5 milliamps, which is 3 volts. And the direction is very important. Remember, I was looking at it for A to be here on the top and B to be on the bottom, meaning VA was greater than VB. So let's look at the direction here. We've got a current in this direction, meaning my voltage drop is going to be in that upward direction. And that's the opposite of what we found. So E Thevenin would have to be negative 3 volts. So that means when I put this together, I have my E Thevenin at 3 volts here. My R Thevenin, which is 2K, found that up here. And then I can put back, I guess, what was over there? RL. It was an unknown resistor, just RL. So this would then be the Thevenin equivalent circuit. And as you can see, this is a much easier circuit to work with if we want to change RL a few times and analyze what happens at RL. That's a little easier to deal with than this original circuit was. And that's the whole value in finding the Thevenin's equivalent circuit there. So what other options could we have used for solving this? Well, we could have done mesh analysis, for instance. So made this I1, made this I2, and let's work on this. So if we did mesh analysis, we would have, let's see, 4.8K times I1 minus 4K I2 equals, and it looks like that's a negative 6 minus 10. And then my second equation would be minus 4K I1 plus 10K I2. And then we have just the 10 volts, the positive 10 volts there. So I'm going to plug this into my calculator. Hopefully it won't take too long. Again, sometimes I like to work things a couple different ways just to check myself. And we have so many tools now that we really should be doing this for just about everything. If you're not quite sure you did something right, try a different way and see if you get the same answer. If you do, chances are great you did the right thing. So I1 negative 3.75 milliamps. I2 that's negative 0.5 milliamps. That's much smaller. So where are those in our circuit? I'm going to go back up to the original drawing. So I1, wrong direction because it's negative, right? So that's actually going to be 3.75 milliamps. I2 is also the wrong direction, and it's over here, so 0.5 milliamps. And notice that's actually the current through the 6K ohm resistor. So if I multiply the 0.5 milliamps times my 6K, surprise, surprise, I get 3 volts. The 6K is 3 volts in that upward direction again. So since I found it that way, there's a great chance that this is right. So I found it 2 different ways. You could also try superposition. And I think just to review, let's do superposition. That's not a problem. Well, the problem is going to be redrawing the circuit. So let me try redrawing the circuit real quick here. There's our 6-volt source and my 10-volt source, my 6 ohm resistor, 10k ohms. And what did we have there? 4k. Okay, so let's do superposition as well, just because we're practicing all of our circuit analysis techniques on this one problem. Okay, so superposition, if I'm looking for the voltage drop here, or V, actually let's just call it E Thevenin, that's what we're looking for. If we're looking for the voltage drop across that 6k ohm, supposed to be a k ohm resistor, let's find it first due to the 6-volt source. Okay, so we're going to set our 10-volt source to 0, and meaning that we just short it out right there. Okay, so this time we're looking for E Thevenin prime, right? Because it's just due to the one source. So this is really a series parallel circuit if we want to reduce and return. So we would combine our 4K and our 6K here. So that gives us 2.4, and then our total is 2.4K plus 0.8K, or 3.2 kilo ohms of resistance. So that means that our source current, I sub S, would be the 6 volts divided by 3.2K. Which is 1.875 milliamps. And that would be in this direction. Now that would split between the 4K and the 6K, but you know, if I had done what I tell all of my students to do, and that is to redraw the circuit multiple times, we would also see that we have that 2.4K out here. And really, once we have the current here, 1.875 milliamps, that's going to give us not only the current, the voltage across the 2.4K ohm resistor, but also E Thevenin prime, because that's the same voltage that we have across that 6K ohm resistor. Okay, so the voltage drop across the 2.4K, which happens to be E Thevenin prime, is that 1.875 milliamps times 2.4K. And that is 4.5 volts in that upward direction. Now, we need to find E Thevenin due to the 10-volt source. So I'm going to short out the 6-volt source now. And put back my 10-volt source. And it's basically the same problem, just a little bit rearranged. All right, so in this case, now we've got the, our RT would be the 0.8K in parallel with the 6K. And then I would add that to the 4K to get my total. So 800 having some trouble typing into my calculator today. Sorry about that. Okay, so we've got this is 705.88 ohms plus 4,000 ohms. So that means that our source current would be 10 divided by that RT. Which would be 2.125. milliamps. And that current is going this way. So again, if I had redrawn the circuit, I think I'm showing all of my bad habits here of skipping a step. That what we had here was our 4K and our 705.88 ohms right here. We've got 2.125 milliamps here. So the voltage drop right here would actually be the E Thevenin prime that we're looking for, or E Thevenin double prime in this case. So it would be the 2.125 times the 705.88. Or about 1.5 volts. And that is in the opposite direction. Okay, so the 4.5 we found up here was due to the current going up, so that drop was in that upward direction. And for since the current in the second part, just due to the 10 volt source, is going down, that's 1.5 in the opposite direction. So E Thevenin would be 4.5 minus 1.5, or 3 volts, which is what we found before. Now you don't have to work this 3 ways. You pick the way that you are most comfortable with, the way that you think will work the easiest or give you the most accurate results without making mistakes, and you go with it. So a few different ways we found that that would be our Thevenin equivalent circuit for this particular circuit.